Last Tuesday, an unknown hacker sent a series of malicious transactions to 3 separate Ethereum ICO contracts and managed to steal $32 million worth of Ether. The transactions exploited a bug in the Parity Multisig Wallet contract. But what was this bug exactly? How was the attacker able to exploit it? And what does it mean for Ethereum going forward? I'm going to break it down right now. First, let's look at what the Parity Multisig Wallet was. A multisig is a common pattern with cryptocurrency to require the authorization of multiple users in order to initiate a transaction. In Bitcoin, multisigs are implemented off-chain, but with Ethereum, they are commonly implemented in the form of smart contracts. You can code the multisig wallet logic directly into a contract, deploy the contract onto the network, and then store Ether in the contract itself, requiring multiple users to send transactions into the contract in order for the contract to send a transaction. In fact, the simplicity of implementing this kind of logic was one of the original selling points for Ethereum in the first place. On January 19, 2017, Parity Technologies released version 1.5 of the Parity wallet. Parity is one of the 2 major Ethereum clients along with Geth. Part of this release was a native workflow in the attached user interface for creating multisig wallets. So I'm going to start a Parity node on the Coven test network and pass in the flag UI, which will automatically bring up the user interface. Pin that to tab 1. And if I look at my accounts, I'll see that there's this button for creating a wallet. And if I click on this, the default option is to create a multisig wallet. So if I click next, it's going to ask me to fill out configuration for this. So I'll just call this test wallet 1, test wallet 1. And it needs the contract owner of the account. I'm going to use this Decipher Media account because that's the only one with Ether. And I will put on 2 other owners on this wallet. I will put this thing called OG MetaMask, which was my original MetaMask account, and then this thing called Snakes, because literally the password to that account is just Snakes. And I'll say that it requires 2 owners, and then there's some massive limit in Ether that each owner can spend. But this multisig wallet that I'm about to create would require 2 out of these 3 signatures to ever transfer any Ether. And I hit create, password to unlock the account. And then it deploys the wallet to contract address here. So if we pop open the Covan Etherscan instance and put in that contract address, we'll see that we do have a contract deployed on the Coven test network, and the source code of it is right here. So I'm gonna go ahead and grab this source code and paste it into Atom so that we can look at it in a little bit more depth. The first thing to note about this code is that there's actually multiple contracts being defined. There's this contract called wallet that starts at line 397, but also if we scroll up, there's this other contract called wallet library that starts at line 66. So what exactly is going on here? In Ethereum, you pay for the bytecode that you use each time that you deploy it. So in an effort to save on gas costs, because this contract would constantly be deployed, Parity abstracted part of it out into a shared library that it deployed exactly once. And then each time a new wallet contract was deployed, it could just reference that shared code. That's what this wallet library variable is referencing. Right here, this D7EE, this is the address of the deployed wallet library contract on the Coven network. So if I go back to Etherscan and typed in this contract address, you would see that this contract source is the actual wallet library code. And then we could call out to this library from each individual wallet instance that's deployed. And the way that Parity was choosing to call out to that contract was by using this opcode called Delegate Call, which you can see here in wallet library.delegate call. Now, what Delegate Call lets you do is it lets you call out to another contract that's deployed on the network, but it lets you call that contract while preserving the call context of the current contract that you're in. And by call context, I mean things like message.sender. So like that message.sender variable will be the account that is calling this contract here, as opposed to the contract calling this contract here. And this is very similar to doing something like .bind this in JavaScript, where you're calling another function, but you're passing in the current call context of the function that you're in when you're calling out to that. And delegate call is an opcode that is created to do exactly this. This is a completely reasonable use case for it. But what ended up happening is that there were 3 separate things that all went wrong that allowed this use of delegate call right here to be exploitable by the attacker. So the function that's going to get hit in the attack is the init wallet function on the wallet library. And the init wallet function is what is used to initialize the wallet by the library when you first create it. And there's 3 problems that all went wrong simultaneously that allowed this to be exploitable. Problem number 1 is that there's no guard present in this function. So init wallet, you should only be able to call this if the wallet is not already initialized, because you don't want anyone calling init wallet once the wallet's already been created. Well, guess what? There's no guard here. It just inits the wallet. It doesn't check whether or not the wallet has already been initialized. So that leaves it exposed to being called again if you could get access to it. So this leads us to thing number 2 that went wrong, which is the scope of the function right here. So in Solidity, there are 3 kinds of functions, right? There's public functions, there's internal functions, and then there's private functions. And by default, functions are public, which is interesting in and of itself. But by public, I mean that anybody can call this function. So anyone can make a call to this wallet library and call the init wallet function. If the function was internal means that there's only 2 people that can have access to this function. There's this contract itself, but there's also what's called a derived contract. A derived contract is any contract that's created by this library. So for example, that wallet contract is actually created by the wallet library. So this becomes a derived contract of the wallet library, and that means that the wallet can call this init wallet function. Well, that would be really good because remember that the wallet contract was using delegate call to actually call into this library, which means that if an attacker was trying to call this wallet contract, then the context of the call would be from the attacker's address, which means that it wouldn't have access to this function if it was declared as internal. And if the function was declared as private, obviously that means only this contract has access to it and no derived contracts could even call it. So not only should there have been a guard, but there also should have been a declaration on the contract of internal to make sure that the attacker couldn't have had access to it. The third thing that had to go wrong was back in the wallet contract itself, they're using the fallback function right here as some sort of catch-all mechanism to delegate calls to the wallet library. So remember, the fallback function is what gets called if you call a contract, but you don't specify a method that the contract knows about. So this is saying that if you send Ether to this contract, but don't define a method, well, then it's just going to deposit Ether in the contract. But if you don't have any Ether with the contract call, it's just going to delegate that call to the wallet library. So now we have an attack vector into the wallet library from the wallet. And again, now we have trouble on our hands because we have an attack vector in, a function that to init the wallet that's not guarding against whether or not the wallet's already been init, and it's publicly accessible. And this spells trouble. And sure enough, that's what ends up happening. So if we look at the first contract call made by the attacker, it's a call to init wallet on the Swarm City contract address. And I'm going to recreate this attack from scratch on that example multisig that I made on Kovan, just so it's completely clear what's happening. But first I want to explain something that might be a little confusing, which is why there's 5 params in this contract call if there's only 3 parameters in the contract. So this requires a really quick primer on how TX data is created in Ethereum. So whenever you call a contract, you need to send some message data, right? And that message data is going to consist of a few things. First, it's going to consist of a 4-byte signature of the method ID. So 4 bytes of the method ID. And then each parameter of the method is going to be 32 bytes exactly. So a bunch of 32-byte strings of the params. So for example, in init wallet, so this is init wallet is the function that we're calling. This is going to have 3 parameters. It has a vector, right, of the owners, and these are addresses. Then it has an integer of how many of those owners are needed to make a transaction. And then it has another integer of what like the daily spending limit of the contract is. And this is 3 parameters, 1, 2, 3. But arrays are a little bit confusing when you use them as parameters, as we'll see in a second. So normally this would go, okay, so we have 4 bytes for the method ID, and then we have 32 bytes of param1. And then we have 32 bytes of param2. And then 32 bytes of param3. The problem with this is that with arrays, you need to declare what their length is. So not only do you need to put the arguments to it, but you need to make a declaration of what the length of an array is, and this can take more than 32 bytes. So instead of actually putting the array arguments at the beginning of param1 where they should be, we're actually going to put the arguments to the array at the end. So param1 is, instead of actually having the arguments to the array, it's going to contain the offset in bytes of where the arguments to the array start. So param2 will just be a 32-bit integer. Param3 just be 32 bytes of the integer. And then starting at param4 will be the length of the array of 32 bytes. And then param5 will be the first argument to the array. And because this is an argument, this is an array of addresses, the attacker, what he will do is declare of length 1 and then pass in his address as the argument to the array. So there's going to be 5 params total, and then this first parameter here, if we go back to the actual attack, you'll see that the first param is 60. And because this is hex encoded, that corresponds to 96. And that would be because 32 bytes plus 32 bytes plus 32 bytes is 96, and then that's where the arguments to the array start, which is 1, and then the first argument to the array is the attacker's address. So if we look at that multisig that we have deployed on Kovan, we can see that there are 3 owners declared on that contract, and we could look at them by using this getOwnerQuery method. So owner 0 is C46, the next owner is 5C7, and then the third owner is 00E, and it requires 2 of those 3 signatures to execute. And then if we queried for another owner, it would just be empty. So we are logged in right now as owner DC0. So this guy is not defined on the contract. This is going to be our attacker, and we're going to try to get DC0 access to this contract. Okay, so I'm going to create a new array called data, and then I'm slowly going to push data into this array to build up the attack data that we need for the attack. So the first thing we're going to need to do is get that 4-byte method signature. So remember, the function that we're calling is init wallet, and it's going to have 3 arguments, and an array of addresses, a uint 256, which represents the number of owners you need, and then another uint 256, which is going to represent the spending limit of the account. And we can get the method signature by taking the SHA-3 hash of this and then taking the first 8 bytes. First 4 bytes rather, first 8 hex characters. And then we can data.push this onto the array so that we have our first item. The next thing we're going to need to push is that first argument for the array, but remember that's going to be a byte offset of exactly 96 bytes. So we could do web3.2 hex and then pass in 96, and we'll see that we do get ox60.substring 2 just to get the 60, and then we need to pad this so that it's exactly 64 characters or 32 bytes. So we can just do 0.repeat62 plus this, and then data.push. So right now our data array looks like this. The next thing we're going to need to push on is the number of owners required. In the attack that the attacker used, he just used 0 for this. So we can data.push 0.repeat64. And now our attack data array looks like this. The next thing we're going to need to push on is the daily spending limit of the wallet. So I think this can just be any arbitrarily high number. Web3.2 hex, Web3.2 way, 10 million maybe. Because there's a lot less than 10 million ether, and it's going to be some number like this, .substring 2, and then what's the length of this is 21. So we can then do 0.repeat 64 minus 21. plus this, which will be something like this, and then we'll data.push that. And now our attack data looks like this. Now we need to actually encode the arguments to the array. So the first argument is just going to be the number 1, because we just want to declare that the length of the array is 1. So we can data.push 0.repeat 63 plus 1. Sorry, and now our attack data looks like this. And then the final thing we're going to need to do is push on the address of the attacker. So the address is going to be exactly 40 characters. I can just access it like this. So we're going to data.push 0.repeat 20, or 24 rather, sorry, plus decipher.account.substring 2. And right now, our attack data looks like this. So now we're just going to join this array together and do var attack data equals data.join. And right now we have a malicious hex encoded string in the proper format to send with the transaction that should give us access to the wallet. So now I need to encode that attack data into a transaction. So I'm going to make a variable called rawtx. And this needs a nonce, which we know will just be 0 because this is the first time I'm ever using this account. We need to send to something. So let's go get that contract address that we're going to send it to. This will be from the account that we are currently logged in as. Then we need to set the gas limit, which I'll just make web3.2 hex on. Let's make some number like 3, I don't know, 2 million maybe? 3, 1, 2, 3. That should be enough. The gas price, we can just use whatever the default price on the network is, which we can get with web3.f.gas price. And then finally, we're going to need the data, which we know is this malicious attack data that we have already constructed. And that should be good. So we should have this rawtx object. And now we just need to sign this with our private key and transact it. So we can make a new tx with this ftx library on the rawtx. And then we can sign this with our private key, which I have accessible here. And then we should be able to tx.serialize and turn this to a string. And right here is the malicious transaction data that we can send to Coven that should give us control of the wallet. So let's go ahead and try that. Let's do web3.f.send raw transaction. And I think this will need to be prefaced with a 0x probably. And then this takes a callback function of error tx hash. And let's just console.log that tx hash out. So there we go. This should be the malicious transaction hash. And if we go into our Coven Etherscan instance and search for it, it looks like we did send this malicious transaction to this contract with, and if I go back for a second, you should see that the init wallet function and the attack data should look very similar to what the actual attacker did on the mainnet. So now if we look at the contract and try to read it, the number of owners has decreased. And if we look at getting the owners, DC0 is now the owner of this contract. So that's all that it took. Everything that I just did in a couple minutes right there is all that the attacker needed to do. And now he's sitting on, 30 something million dollars. So what ends up happening is that there are 3 multisig wallets that are hit. And they're the wallets holding the ICO funds for Swarm City, Eternity, and Edgeless Casino. All 3 of which happen to have infinity logos, immediately prompting conspiracy theories about what any of this is supposed to mean. And also, by the way, super clutch by the team at Dfinity for not using the Parity Multisig Wallet. I mean, you've got an attacker hell-bent on bringing down Ethereum holders with infinity logos, and your name is literally Dfinity, and you somehow avoid it. Good job over there. Anyway, because the bytecode of all the contracts are public, you can run analysis and find contracts with similar bytecode to each other. So once news of the attack became public, which was almost instantaneously, it was possible to immediately find a full list of every contract on the Ethereum network using the Parity Multisig Wallet. And then things get strange. So what happens is that allegedly a group of white hat hackers, aka good guys, proceed to drain the remainder of all the vulnerable contracts with an automated script. And this amounts to something like $85 million worth of Ether being drained. and then through some sort of back channel communicate to the Ethereum Foundation that they're actually going to return those drained funds to the rightful owners. And this is possible because you can redeploy the multisig wallets with an updated patch and the same parameters that they were configured with before and resend the ether to it, and it's just like the hack never happened, only it did. And the Parity Multisig code, by the way, is immediately patched. You can go ahead and look at the commit here on GitHub. This is by Gavin Wood, and you'll see that the patch consists of adding an internal declaration to the init multi-owned function that is called by init wallet, and then also adding a guard to init wallet itself to only allow init wallet to be called if the wallet is not already initialized. So there are a couple takeaways from all of this, I think. First is programming related. The attack itself can accurately be described as poor language design in Solidity. It's giving programmers too much rope to hang themselves with. Everything with programming languages is a trade-off of some capacity. So having user-defined functions being default public like they are in most programming languages is a trade-off to make the developer experience better, but it comes at the expense of security potentially. And normally I love making this trade-off. Trading off towards developer experience is why I love languages like Ruby and React Native and products like Heroku and on and on. But even I'll admit that when you're writing financial contracts on Ethereum, you need to trade off way harder against developer experience and towards security. Security is everything with Ethereum development, and I honestly don't even care if it's the most challenging experience in the world to write smart contracts. Like, I'll deal with it. I'm sure most developers will deal with it, as long as exploits like this are not possible or mitigated to every capacity that you can even think of. So you'll probably actually will see a move in the future towards things like default private functions or internal functions in Solidity, and I am totally cool with that. That needs to happen. Another suggestion that I found interesting from the Parity team was to require developers to add guards to all functions. So most smart contracts are state machines of some capacity, and I'm still thinking about how this would work in practice, but it might be a good idea to actually require that developers whitelist the specific state of the contract that each function is supposed to be called in. So for example, in the Parity Multisig, Solidity itself could require you to specify that the init wallet function is only allowed to be called if the wallet had not already been init. And that would have prevented the attack, because it could be, you know that init wallet function should only be called in one specific state, so the compiler could enforce that you need to declare what state it can be called in. That could be interesting. I also think this is a little bit of a lesson in unnecessary complexity in code, because, I mean, why does the default multisig implementation deal with things like daily spending limits? That seems like unnecessary complexity. That's a feature that may or may not need to exist. But when you're dealing with core infrastructure, it should really be as simple as possible, because I mean, you need more people to read it. And it's going to be an interesting question. How do you get as many eyeballs as possible on these contracts to find and mitigate issues as soon as possible without having the ship blow up in order to discover them? So keeping code small seems really important, because it'll incentivize more people to try to wrap their heads around it. And obviously, exploits like this are not unique to Ethereum. They're littered in core infrastructure all over the internet. But what is happening is that the liquidity market, from the exploit itself to like financial returns, is just so simple, quick, and efficient that it's almost unprecedented. And that's going to just drive a lot of malicious attackers towards systems like Ethereum. I mean, like, look at the implicit bug bounty on these things. Someone found a bug in one code base and immediately got $30 million in somewhat liquid assets as a reward. I mean, that's insane. The hackers are definitely coming for this stuff. And I'm also kind of curious who this alleged white hat hacking group is and under what conditions they're agreeing to return ether to the Ethereum Foundation. Is there like some sort of trade that's being made and what's being traded? I think that there's a story there that requires some explanation, but it is interesting little like political drama. Man, Ethereum is going to be a battlefield over the next year, and I couldn't be more excited to be fighting in this war in some small capacity. So if you want to keep up to date on the latest happenings, give the channel a follow. A lot more content coming your way soon. Peace.